I'm going to show you some transformations. Transforming what? Well, if you don't mind, we're going to transform my portrait. Let's begin with something simple. The transformation z goes to z over 2. Each point on the photo corresponds to a complex number z that's divided by 2. We get another point. It's imaged by the transformation, hence a new picture. You see, no surprise, I just shrank to half the size, since each z has been divided by 2. This transformation is called a homothety. Let's go to the multiplication by I. Easy! We know that multiplying by I is just a quarter turn. Note that the modulus does not change, but the argument increases by 90 degrees. Indeed, this is quite a sophisticated way of saying that we just rotated the picture. Well, a bit more complicated. Multiplication by 1 plus I. Look at the complex number 1 plus I. It corresponds to the point with abscissa 1 and ordinate 1. Its argument is 45 degrees and its modulus is the square root of 2, using Pythagoras' theorem. Hence, a multiplication by 1 plus I amounts first to multiplying the modulus by the square root of 2, and then to adding 45 degrees to the argument. In simple words, one has to combine a homothety and a rotation. This is called a similarity. More interesting. We are going to transform the points z into their squares, z multiplied by z. Let's begin by placing the photo in a suitable place, flush against the coordinate axes. Then I zoom a little bit, since the squaring process will change the size of things, and I need space to show you this. OK, now we can transform the photo progressively. Notice that the argument of z squared is twice the argument of z, so that the right angle on the lower left of the photo is doubled under the transformation. It has turned into a 180-degree angle. Let me place the photo somewhere else and let's look again at the same transformation z squared. You will notice again the same argument doubling. For instance, look at my index finger. Before the transformation, its argument is about 45 degrees. And after the transformation, it points upward at 90 degrees. But you can also observe that moduli are squared. Now let's go to a new transformation, sending the point z to minus 1 over z. Don't forget, with complex numbers one can add, multiply, but also divide. Not by 0, of course. Doesn't this image remind you of the Sistine Chapel? Large complex numbers with a large modulus become small when one takes their inverses, and conversely. Here is a similar transformation. Look at the formula. The value of k changes slowly. Some parts are expanded, others are contracted, but if one looks closely, the shape is preserved even though lengths are not. A circle remains circular even though it might grow. My hand grew, my face became smaller, but you can still recognize me. One more transformation, more involved. Well, this one is not really a weight loss program for me. But note once more that even though I got bigger, the shapes of small parts did not change. For instance, if you look at a button on my shirt, it keeps a circular shape. One says that these transformations are conformal or holomorphic. Rather complicated Latin and Greek words for saying that one preserves shapes. Indeed, with complex numbers, one can do quite a lot. One can even take the exponential, if you know what this means. But even if you don't know, look at the treatment I have to suffer from the exponential. Has my head disappeared? No. If you look through a microscope near the origin, you could see my beard. Now that you know about complex numbers, and you've seen some transformations, I will explain some of the objects I've been studying closely. Here you see a number of points. Some are blue inside the unit disk, and some are yellow outside. Let's perform the transformation z squared several times, and let's look at the result. You can see that the blue points stay inside the disk, and the yellow points, on the contrary, escape from the disk, and even escape from the screen. One says that the blue disk is the filled-in Julia set of the transformation z squared. Points outside the Julia set escape to infinity when one repeats the transformation indefinitely. But we can play the same game with other transformations, like for instance those of the form z squared plus c, where c is a complex number that we can choose at will. For each complex number c, we therefore have a Julia set whose shape changes when c changes. You can see a few examples here. Here is the one I called the rabbit. In order to understand how these shapes change, I will show you several things in parallel. On the left-hand side, the red side, you can see a point that will start to move. This is the point C. On the right-hand side, you see the corresponding Julia set. This is deforming as C slowly changes. But sometimes, for some values of C, the Julia set seems to disappear. One cannot see anything anymore on the screen. Like now, for instance. The truth is that the Julia set blew up into an infinite number of pieces so small that you don't see anything on the screen. Benoit Mandelbrot, who popularized fractal sets, suggested the study of this set, drawn in red, that describes the values of C, for which one can see the Julia set clearly on the screen. In other words, those for which the Julia set did not blow up into multiple pieces. Of course, this red set is called the Mandelbrot set, and I spent quite a lot of time studying it. To finish, I suggest that we look closely, very closely, at this Mandelbrot set and zoom inside so that you can appreciate how beautiful it is. Let's go. Here it is. Admire. For once, I will not explain everything. Imagine the Mandelbrot set as a black island, surrounded by a tropical sea, and that you can see the bottom of it. Really, you are looking at truly microscopic details. If the Mandelbrot set were the size of a soccer field, well, we would be looking at details the size of a single atom, of the order of a millionth of a millimetre. Maybe you're wondering why I got interested in this. First of all, because it is beautiful, and because understanding these objects gave me much pleasure. For me, this is reason enough to spend time on these questions. But also because in these transformations that look so simple, one can find the essence of chaos, such a fundamental concept in modern science. Simple things generating rich structure. To study complicated phenomena through their simplest incarnation, this is often the role of the mathematician.